Hello everyone. Today let's solve the problem digit tree. So this was asked in the Codeforces around 372 for the division 1, right? So this is basically difficult question, I believe. It's rated 2700. Yeah. So let's see what the question states. I'll just summarize the question so that it will be easier for us to solve the problem. You can just go through the question, man. It's easier to understand. As I've said, I'll just summarize the question so that it will be easier for us to solve the problem, right? Let's see what the question states here. Just give me a second here. Yep. We are given a tree with n vertices, right? So we are given a tree with n vertices and the digit from 1 to 9 on each edge, on each edge, right? So we are given n vertices. We are given a tree with n vertices and a digit 1 to 9 on each edge, right? So we have to choose the ordered pairs. We have to choose the ordered pairs u comma v such that u is not equal to v, such that u is not equal to v. U shouldn't be equivalent to the v. For a pair, we have to read it. We have to read the digits. For a pair, we have to read the digits along the shortest path from u to v, along the shortest path from u to v, right? Again, for the pair, we have to read the digits along the shortest path from u to v in order just to form the decimal integer, just to form decimal integer. This is fine. Now, what we need to find then, what is our main job here? We have to count how many ordered pairs. We have to count how many ordered pairs. This one, we have to count how many ordered pairs produce a number that is divisible by m. Number that is divisible by m, right? So given GCD of m comma 10 is 1, right? So given GCD of, see here, m comma 10 equals 1. Just remember this one, right? So we need to count how many ordered pairs produce a number that is divisible by m, right? So that's what we need to find here. Again, let me read the question loud. So just listen to this carefully. So we are given a tree with n vertices, right? So we have given a tree with n vertices and a digit 1 to 9 on the each edge, on the each edge. So we have to choose the ordered pairs u comma v such that u is not equal to v, right? For a pair, read the digits along the shortest path from u to v. For the pairs, we have to read the digits along the shortest path from u to v in order to form a decimal integer, right? So we have to count how many ordered pairs produce a number that is divisible by m, given GCD of m comma 10 equals 1, right? So this is the question basically, right? So let me come to the example part here, or the input output part here. So we have been given n equals 6 here, m is 7, n and m we have been given 6 and 7, right? So this is nothing but n and this is nothing but m, and these are the edges basically. So here 0 to 1, 0 to 2, 0 to 3, 4 to 2. So this one, see this one, these are the edges basically. This first two numbers are there, right? So these are the edges, and this is the value. So this is the value towards the edge, right? So we can consider this one as the directed graph basically, right? So this is fine. These are the values basically in simple terms, right? So we can just represent in this way, man. So we have from 0 to 0 to 2, we have 0 to 1, 1, we have 0 to 2 as well. So we have 0 to 3 as well, and we have 2 to 5, and this one, what do we call? 2 to 4 and 2 to 5 we have, right? Yeah, 2 to 4 and 2 to 5 we have here, right? So we can just represent in this way. And the values for 0 to 1, uh, we have here this one, right? 0 to 1, we have the value 2. 0 to 2, we have the value 1. And 0 to this one, 3, we have the value 9. 2 to uh, 2 to 4, we have 4. And 2 to 4, we have 4, yeah, and 2 to 5 we have the value 7 basically. Yeah, this can be represented in this way, right? So this is the, it can be represented in this way, the tree, right? So this is fine. So these are the values. The first two this one numbers are nothing but here this one edges basically. right? So they have given here 0 to 1, 4 to 2, 2 to 0, 3 to 0, and 2 to 5. It can be represented in this way, right? So it just, this is fine. So now let's do one thing. The output that we need to get here is 7, right? So how we'll get 7? That let's consider the same example here, the first example for the approach as well, so that we understand the this one approach correctly, right? So now we have the understanding of the question what we need to do, and we have the understanding of the input output as well. Let's do one thing. Let's quickly discuss the approach followed by the complexities, and then let's write the code. As usual, let's discuss the approach first. So I have considered the same first example that they have given in the question, right? So this one we know this is nothing but nm. So these are the edges and these are the value for the edges basically, right? So this is fine. The output that we need to get here is 7, right? So let's move on with a step-by-step explanation here. So this I have already shown actually. We have been given nm and the edges. I have already done this one and show. I have showed I have showed already this one. This is fine. Now let's move on with a step-by-step explanation. So first what we will do, we will list the ordered pairs basically from U to V that produce the numbers that is divisible by 7. Initially, let's consider 0 to 4, right? 0 to 4. So we are considering, we are listing the ordered pairs from U to V that produce the number divisible by 7. So we can consider 0 to 4. So path will be from 0 to 4, path has to be, see here. We have to move from 0 to 2, then we have to move from 2 to 4. So this one is 4 man, not 2. Sorry, from 2 we have 4 here, right? So I got confused, I believe. This is fine. Just one correction, that is 4. So we have to move from 0 to 2, then we have to move from 2 to 4, right? So the digits are 1 comma 4. The digits are 1 comma 4, nothing but we are considering value here 1 and 4, right? So the digits are 1 comma 4. So we'll get the number 1 4, right? So 1 4 will be going with a 1 4 modulo 7 as we need to use the mod. So this one remainder will get 0. Same thing we will do for all the ordered pair list, right? So next we will consider 1 to 2. So see here, for 1 to 2, so we have to go with 0, 102, right? So we have to go with 102, right? So we'll be going with a path 102. So this one we can go in this way, right? From 1 to 2, from 1 to 0, then 1 to 2. Basically, we have to consider the values 2 and 9 here. 2 and 2 and 1, right? Yeah, this one we have to consider. Sorry, 9 is for the 0 and 3. So 2 and 1 value we have to consider here. So the number will be 2 1. So 2 1 modulo 7, nothing. Again, the remainder is 0 here. Same goes with the 1 to 5. You can check path for the 1 to 5. We have here 1 to 5, right? So we need to reach 1 to 5. So we have to go first 1 to 0. 1 to 0, then 0 to 2, then 2 to 5 basically, right? So 1 to 0 we have the value 2, 0 to 2 we have the value 1, 0 to 2 we have the value 1, and 2 to 5 we have the value 7. So this one will be 217 basically, right? Yep. Yeah, 1025 and the digits 217. So this one 21 modulo 7. So this is divisible. 217 is divisible by 7. So again we get the remainder 0. 3 steps we have covered, right? So 1, 2, 3. Let's move on with the next list of ordered pairs. So nothing but from 2 to 5. 2 to 5 it is directly reachable, right? So this is fine. 1 second. 2 to 5 it's 7, right? 2 to 5 it's again 7. 7 modulo 7 is 0, and this is the fourth step. 4 times we have done. 5 to 2. 5 to 2 again the same thing. 2 to 5, 5 to 2 is again the same thing. So this one will be 7. 7 modulo 7. So this one is fifth step. 5 times. So now 3 to 2. 2 to 3. So 2 to 3 we have to go, right? So this one will be 2 to 0 and 0 to basically 3. So this one will be 2, 0, 3. Again, we will be going with a 1, 9. The values 1 and 9 basically, right? So now here, yeah, 302, 9 and 1. So this one will be 203 or 302, both are same one. So 9, 1. So this one 9, 1 modulo 7, we get the value 0, right? So 91 is divisible by 7. Again, the final one here is this one, 3 to 5. 3 to 5 we have already checked, no? So 3 to 5 it is, yep, 3 to 0, then 0 to 2, then 2 to 5, right? So we have to go with 917, 917, right? So let's check the same whether we are going with 917. Yeah, 917, 3025. 917 modulo 7, it is divisible, and this one is the last one. Basically, this one is sixth one, and this one is 7 times we have done. Total is 7, right? So we have 7 interesting ordered pairs, right? So we have 7 interesting ordered pairs basically, right? We got 7 here, 7 times, right? So we have 7 interesting ordered pairs. So the final output that we got here is 7, right? Final output that we got here is 7, which is equivalent to the output that they have mentioned for the example 1 within the question. So our approach works absolutely correct. As we are completely familiar with the approach, let's discuss the key idea as well. Before moving into the complexities part, let's discuss the key idea as well. So how we will be writing the code basically, right? So the first step here would be just listen to this. While writing the code, you'll understand this one, what we'll be doing basically, right? So first what we'll be doing, we'll be pre-computing the PW of I that is equivalent to the 10 to the power of I mod m, right? So next part would be for each node, that we consider, right, we will be storing two modular values. One is dn of u and another one is up of u. Dn of u is nothing but value when reading the digits from root to u. Value from when reading the digits from root to u. This you will understand, this you will get it when we write the code. And up of u is nothing but value when reading the digits from u to root. That one dn of u is nothing but from this one root to u. This is from u to root, but this one stored aligned for the quick concatenation with the other halves basically, right? So this is when the second one is for each node we'll be storing two modular values. So we will be going with a modular arithmetic here, right? Also we'll be going with a modular inverses. Might be we'll be going with the Fermat's little theorem, or we'll just be making use of the modular inverse. That we'll be seeing within the code itself when we write the code. So we will be making use of the modular inverses as well, and also we'll be calculating the GCD, right? So here, since in the question they have given GCD of 10 comma 1, 10 comma m is equivalent to 1 basically, right? So they have given 10 comma m this one is equivalent to, not minus here, this is, it is equivalent to 1 to align the place values when matching the halves, right? So we'll be going with the, again we'll be going with the modular inverse as well, the number theory basically, and GCD as well. So pre-computing values, then modular inverse as well, number theory. Here again we'll be going with the GCD as well, calculating GCD as well. And then Euler's GCD formula will be going with. Then we will be making use of the DSU on the tree, nothing but disjoint set union on the tree with two hash maps, right? So again, we'll be making use of the hash maps as well, two hash maps U and D, just to count the complementary residues efficiently, right? DSU along with the two hash maps here. So overall, what we'll be making use of to solve this particular problem, we'll be going with the pre-computation, modular inverses, we'll be calculating the GCD, as well as we'll be going with the DSU along with the two hash maps, right? So basically this is the idea. This is the idea. The problem is going to be huge, and this is the idea. Let's see that one when we write the code basically. Before writing the code, let's discuss the complexities part as well, man, right? So what will be the time complexity here? The time complexity would lead to big of n log n. So why it is n log n here, the time complexity? So the time complexity here would be big of n log n, because why it is log n here? So because we'll be making use of the DSU on the tree, right? So we will be going with a disjoint set union on the tree that merges the produce near linear behavior. And one more thing, each node processed a small number of times here. Effectively, we can consider big of n with a small overhead, right? So basically, this is dominated by the tree traversal and the map operation. So overall time complexity would lead to big of n log n. Clear? Now, what will be the space complexity? Space complexity would lead to big of n for the arrays plus big of n for the extra for maps in the worst case, right? Overall, we can just write it as big of n here, the space complexity. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n log n and big of n respectively. Now, as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. I'll just come to the one compiler here. So we'll be making use of the different, this one, fast input and the output. So let me import here, input output package, right? So now we'll be making use of the different utilities as well. I'll just go with, let me import the utility package as well. As I've said, let's make use of the class here. We have to go with the class and at any cost. So I'll just go with the main here, class name main. You can just go with any class name that's relevant to the problem, right? This is fine. Now, the first step here, we would be going with the max array size, right? So let's consider slightly above the constraints. I'm speaking of the value, right? So I'll just go with the static here. This one final int n equals, so 1 followed by 4 zeros and 6 basically. This is fine. The next step would be, let's go with the number of vertices and the modulus m and the answer accumulator, right? So let's go with the number of vertices. So this will be static int n. Also, let's go with the modulus m and the answer accumulator. So this one will be static long m and also answer, right? So this is fine, man. Now let's do one thing. Let's go with the PW of I that is equivalent to the 10 to the power of I modulo m, as we had discussed this one in the approach, right? So UP of U and DN of V, this will store the two modular values for the node. Let's do one thing. Let's go with the initialization part, the same thing. So I'll just go with static here, long PW equals new long of size n. So this is fine. Next one, let me consider variable up here. This one also new long of, let me pass n here of size n. Finally, we had considered dn within the approach, right? Let's consider the same variable name here, new long of n. Let me pass n here. This is fine. Now let's go with the sizes, Heavison and the depth arrays for the DSU on the tree, right? So this is when I said Heavison, this is nothing but the heavy child technique. We also call this one as heavy child technique. If you don't know this, you can just Google it. It's easier to understand, right? So I'll just go with static here. This one int sc equals new int of n. This is fine. I'll just go with sun equals new int of n. This is also fine. Finally, dep equals new int of n. This is also fine. Now let's go with the adjacency list. Each element is an int, right? So it consists of the neighbor and digit, right? So this one, let me go with the static. So let me go with the array list. So this one will be int. We go with g equals new array list of n, right? So this is fine. So let's go with the U and D that maps basically store counts of the modular residues for combining halves, right? So that's what I said within the approach as well. We'll be maintaining two hash maps, I said, right? So let's initialize the same thing. I'll just go with the static here. Let me make use of hash map. So this one will be long. Let me go with the integer. mm, U equals. This is fine, right? Yeah. Let me give here new hash map. Finish the syntax here. This is fine. D equals new hash map as well, right? This is fine. The next step would be we are done with the initialization part. So now let's extend the GCD routine just to compute the coefficients. So we'll be making use of the modular inverse, right? For that purpose, we'll be extending the GCD routine to compute the coefficients, right? So static. So this one long, let me make use of the helper method x GCD. So this is fine. Let me go with the parameters here. A, v as well as long this one xy. This is fine. So within the xgcd method, let me go with a simple if condition. If b equals 0, then xy of 0, let me assign this one to the 1. Xy of 1, this is equivalent to 0. And finally, mm, let's go with, let's return something. Let's return a here. This is fine. Next, let's go with the recursive extended GCD. So this one will be long G equals GCD of B, comma A. So this one will be A modulo B, comma XY. Right. So this one will be long X equals XY of 0, Y equals XY of 1. This is fine. The line number 21 and 22, what we are doing? Line number 21, G equals XGCD, whatever I have written. So this is the recursive extended GCD. Don't get confused. And the line number 30, 22, sorry, whatever I have written. So this, we are retrieving the previous coefficients here, right? So now let's update the coefficients for A, comma B as well. So this one we can do it in this way. XY of 0. Let me assign this one to Y. Also, let me do one thing. I'll just go with xy of 1 here. So this one will be x minus a by b. This is fine into y. Yep. The final step would be let's return the GCD. So this one will be return G, right? So let me come out of this one entirely. Now let's go with a modular inverse of a modulo M, right? So which assumes GCD of A comma 1, this one A comma M is equivalent to the 1, right? So this one we have discussed. So now let's go with a modulo inverse of a modulo M in simple terms. So I'll just go with static again. So I'll just go with long inverse I and V I'll consider. Let me go with a parameter A, right? So now basically I'll just go with a variable here xy. Let me assign this one to new long of 2. Right? So this will hold x comma y such that a into x plus m into y is equivalent to the GCD of a comma m. That will be equivalent to the 1 basically. Now we have already made use of this one, right? We have already written xgcd here. Let me make use of the same thing here, helper method. So this one will be a comma m comma xy. Yep, we are just computing the extended GCD. Now, x may be either negative, right? X may be negative as well. So we have to reduce the modulo m for that if x is negative basically. So I can just write it in this way. If long x equals xy of 0 modulo m. And one last thing, let's return the x, nothing but a to the power of minus 1 mod m, right? So I'll just go with return x here. This is fine. So let me come out of this one entirely. Now let's go with the first DFS. So we'll be making use of the DFS more than once. So let's go with the first DFS. Why we are going with the DFS here? First, we will be computing the sizes, depths, dn and up values along with a heavy child. Nothing but the sun variable that we had made use of earlier, right? So that one. For that one, we'll be making use of the DFS, right? So let's write this one quickly. Static void DFS. Let me go with the parameters U as well as FA. Right, so this is fine. Now SZ of U, let me assign this one to the 1. Also, let me go with the for loop here. Int E of this one, G of U. Yep. Now within the for loop, what we'll be doing? Let's go with the neighbor V and digit W on the edge UV. So this one will be V equals E of 0, W equals E of 1, right? So this is fine, man. If V equals FA, then what we will do, let me we have to skip in that way. So we have to skip, sorry. So I'll just make use of the continue keyword here. The next step would be we have to go with the depth of the child that is equivalent to the depth of parent plus 1, right? So in this case, depth of the child is nothing but depth of v, which is equivalent to the depth of the parent plus 1. Nothing, parent is nothing but the depth of u, right? So plus 1 here. This is fine. Yep. Now let's do one thing. So we have to go with this one. What do we call? UP of V. This accumulates the digits as the contribution when reading from V to root. And also W into PW of depth of U. What it does, it places the digit V, digit W at the proper power of 10 that is relative to the root. So I can just write it in this way. UP of V. So here this will be equivalent to the UP of U, right? Plus W into PW of depth of U. This is fine. U modulo n. So this one has to be modulo m. Finally, modulo m itself. Right. So now let's do one thing. We are also considering dp of v, dn of v, which is the value of the number obtained when reading the digits root to v. Basically, we had discussed the same thing within the approach. So previous into 10 plus w we can go with along with a mod m, right? So we can just represent this one in this way. dn of v, it is equivalent to the dn of u into 10 plus w, right? So modulo m. This is fine. Now we have written the this one. Let's go with a, or let's recurse basically here. U comma v. This is fine. We are going with the deepest DFS, right? So let me go with your v comma u instead. Now let's add the child subtree size, right? SZ is the variable we had considered earlier. So this one will be SZ of u equals SZ of u plus SZ of v. This is fine. The final step would be we have to track the heavy child, meaning we have to track the largest child. So if SZ of v, this one SZ of v, if it is greater than SZ of son of this one, what do we call u, then what we will do, so we'll go with son of u, this one, which is equivalent to the, yep. Now let me come out of this one entirely. uh, yeah, let's go with a calculation part. Now let's make use of the method named calculation or calc. So calc is nothing but for the node u with the LCA that is equivalent to the LCA, we have to count how many nodes from previously added entries form divisible numbers when concatenated with the used path. We had discussed this one in the approach as well, right? So let's continue with the same. Just give me a second. This problem is huge, man. This problem is extremely huge. So let's do one thing. Let's continue with this one calc method. So I'll just go with void calc. So let me make use of the parameters u as well as LC. This is fine. So within the calc method, let me do one thing. I'll just go with a long inverse PW depth u. So this is equivalent to inverse. So this one PW depth of u. This is fine. Yep. Now let's do one thing. X is computed residue matching, right? S is a computed residue matching. Some entries and U, right? So now let's go with some formula, man. So this formula derives from the this one algebra aligning Dn and the UP values to ensure that the concatenated number, right? Concatenated number, nothing but segment 1 concatenated with a segment 2 that is equivalent to the 0 mod m, right? So let me write this one formula. All right, let me write this formula. This is long. So let me give here long x equals, let me type this one, Tn of LCA, this is fine, into PW of DP, again LCA, this is fine. Mm, let me go with modulo M minus dn of U, this is fine, into PW of, let me go with here, this one of LCA, this is also fine, modulo M into PW of depth of this one, again LCA, this one, again let me make use of the modulo M here, so this is fine, into modulo M, right, into inverse. So what is this thing? Inverse PW depth. So that is what we used, right? So this is fine. U modulo M plus P. This one of LCA. This is also fine. Yep, this is fine. Modulo M plus N. Or we have to go with the M plus M. So where is N? And we haven't made use of that. This one. And so this one modulo M basically. This is the formula that we'll be going with, right? So as I've said, so the next step would be, so we'll be going with, or we'll be assigning this one inverse, whatever the variable name that we consider, to the inverse of this one, PW of, so this one will be depth of LCA, LCA. This is fine. Yep. Now let's do one more thing. Uh, So Y is the computed residue of matching some entries in the D, nothing but the DN map, right? So these derived residues correspond to the other half when concatenating two parts. The same thing we have to go with. Let's make the, let's copy the same thing and make the necessary changes here, right? So let me copy this one entirely, and here I'll just go with the long Y equals this one. So what did I do here? Yeah, let me delete this one. DN of LCA into hmm, so this one is quite different, man. Just give me a second here. Let's do one thing. Let me type this one instead. So this is somewhat different actually. So this is dn of LCA. This is fine into I'll just make use of inversion here, not this one. This one. So this one is, let me give LCA here. This one we haven't made use of it anywhere, I believe. Anyways, so let me go with modulo M here. This is fine. Modulo M. Sometimes I get confused. P of this one. LCA. This is also fine. Minus UP of V. This is also fine. V plus M. Yep. Plus M. Modulo M into this one. LCA. So this one modulo M. Let me leave space here. LCA modulo M into LCA. This is also fine. Modulo M. Mhm, fine. M. M. This is fine. Yep. This is it for the formula basically. Next, what we have to do finally, let's add the counts of the both maps, nothing but u of x plus d of y. So also we'll be keeping default 0 if it is missing, right? So this is simple. Answer equals answer plus. So I'll just go with this one. U dot uh, get or default. This operation that is provided by the hash map. Basically, default x comma 0, right? So plus d dot get or default this one. Uh, let me go with y comma 0, right? So this is it. Let me come out of this one entirely. We are done with the calculation, right? Calculation method or the calc method basically. Now let's go with the add node method, right? So add node method basically what we'll be doing here, we have to or we will be inserting the node use residues into the maps u and do for the future matches, right? Let me go with static here, void add node of this one int u. This is fine. So first, let's go with the residue for the up direction map, normalize DN value, and finally, let's increment the count and up map as well as UP map as well as let's increment the count and DN map as well. Let's do these four things very quickly. X equals UP of U, also Y equals DN of U of this one. PW, so this one will be depth of U. This is fine. Mm, modulo M. Now let me go with u dot put here. So this one will be x comma u. But let me go with the get dot default that is provided by the hash map x comma 0. This is fine. Plus 1. So we're just incrementing the count and up map, right? So let me copy the same thing and make the necessary changes for the d as well, right? So we are going with a u and d. So let me give here d dot put, right? Instead of the x, we have to consider y here. Instead of u, we'll be going with a d here. So again, here as well, we'll be going with a y, y comma 0 plus 1, right? So let me come out of this one entirely. We are done with the add node method as well. So now we are left with two more methods which are very important, right? So just give me a second here. We are left with two more very important methods. That is, one is update and another one is get answer. Update because uh, we have to either calculate this one using the calc method, whatever we have used this one, this method. So we have to either calculate when k equals 1 using the calc for all the nodes in the subtree, or we have to add the nodes when k equals 0 to the maps. Either of the things we have to do. This is used when merging small subtrees into the this one heavy basically, right? So let's go with the update method. Let's go with the update method. So I'll just go with static here, void update. So let me go with the parameters here, u, fa, lca as well as the k. So if k is equivalent to 1, we have to count the matches between you and existing map entries. So I'll just go with if k equals value 1, let's make use of the cal method over here. Let's call the calc method here. So this one will be u comma lca, right? So this is fine. Next, if k equals to 0, then we have to add the u to the maps, right? Accordingly with what we have discussed. So this one will be else. Let me make use of the add node method that we have written, and let me pass the u here. We have successfully made use of the calc and the add node method within the update method, right? So that is the reason we wrote those methods basically, right? So this is fine. Now let's propagate to children. In the sense, let's move on with the iteration part here. So this one will be int e of this one graph basically, g of u, right? So this is fine. This is simple. So let me assign v to e of 0. Yep. The next part would be we have to skip the parent and we have to recurse. When I say we have to skip the parent, let me go with v equals fa, then we have to continue, right? So this is fine. Then finally we have to recurse. Let me go with the update of what are the parameters that we need to pass here? V, u, we need LCA as well along with a k, right? Along with a k. We're just recursing. We are done with the update helper method or the update method basically. Now, what the final method is, we have to get the answer, meaning we'll be going with the get answer method. Nothing but we will be performing the DSU on the tree main routine, right? So this basically computes answer by processing heavy child at the last. So let me go with static here. Void. Let me go with get answer. This is fine. So this one will be int u comma int fa comma int, right? So these are the parameters that I'll be making use of. First, let's process all the light children first, then clear their contributions, right? Let's directly hop into the iteration part here. So this one will be int of graph u, right? So this is fine. So within the for loop, let me assign v to e of 0. This is fine as well. Now, if v equals fa or v equals son of u, then let's do one thing. Let's give continue here. This is fine. We are just skipping the parent and the heavy child. Now let's finally let's solve and clear, right? Meaning we have to keep the this one keep variable itself we have made use of. We have to keep that one to the equivalent to the 0 basically. So let's recurse. I'll just go with a get answer here. What are the parameters that we need to pass? U, v as well as the 0. Right, so let me come out of this one entirely. Now let's process the heavy child and keep its data. So we have to avoid the clearing here. So this one, if son here, son of u basically, if it is not equal to 0, then I'll just go with a get answer. Son of u, this is fine, u comma 1. Yep. Now let's do one thing. Now for the each light child, we have to use its nodes to query against the heavy child stored maps, right? Then we have to add its node into the maps. So future queries will see them, right? In simple terms, let's go with the let's move on with the iteration part one. So this one will be for int this one e of u basically. This is fine. Int v equals e of 0. This is fine. Now if v equals fa or v equals son of u, let's do one thing. Let me give continue here. The next step would be let's go with the update here. So we have to count the matches between v to subtree nodes, right? Uh, how can we write that one? Let's go with the update here. Let me pass v u as well as u here. Finally, 1. And let me go with the update again. So this one will be u v u u as well as the 0, right? So this is fine man. Now let's do one thing. We have to count the pairs when LCA is u and one endpoint is u itself, meaning single node side, right? So we have already written calc for that calc function. Let me pass u comma v, right? So again, let me go with the add node. So we have to add u to the maps, right? So when we this one split this one certain functions into the this one methods, and then we write each functionality into that method, it will be very helpful in this way, right? It will be crystal clear to understand. When someone reads the code, it will be clear to understand as well, right? So we have successfully count the pairs, right? And then we added you to the maps. Now we are left with this one. If we shouldn't keep this subtrace contribution, if we shouldn't keep this subtrace contribution, then we have to clear the maps. For that, let's write the simple if condition, the last one. If keep equals 0, then I'll just go with u dot clear here. Also, we have to go with d dot clear, similar one, right? So let me come out of this one entirely. Now we are done with all the methods. Let's move on with the main method one, right? Let's move on with the main method. So I'll just go with main here. Let me go with main, delete this one. I'll just go with throws exception. This is fine. So within this one, let me make use of the buffered reader and this one. What do we call? Hmm. So let me copy paste this one. This one we have already written the important ones. Let me copy paste this one and let me explain whatever I have done here. So I'll just come here. Let me paste this one. Yeah. This is mostly related to the input output and some of the this one, some of the helper methods that we have written. We have made use of it, right? So this buffered reader and the print writer, it is related to the input output. We know this one, right? So this buffered reader and the print writer. So this is nothing but the fast input buffered reader, and the print writer is nothing but the fast output, right? This string tokenizer, we are just reading the first line here. So see here, uh, n and m we have to read this one, right? So that is the reason we are making use of the string tokenizer here, right? N and m. So that's what we have done here. So this for loop, whatever we have made use of here, this one we are initializing the adjacency list, right? So we are initializing the adjacency list. So this has to be clear. Now we are as per the approach, first thing is we have to pre-compute the powers of 10 modulo m, right? So that's what we discussed in the key idea. If you remember, we have to pre-compute the powers of 10 modulo m. Nothing but we'll be keeping here pw of 0 is equivalent to the 1, and pw of I equals pw of I minus 1 into 10 modulo m, right? So that's what we have done here. That's what we have done here, right? So then again, we are going with one more for loop. So this one, because we have to read the edges, n minus 1 line. So this one, we have to read the edges, right? 0, 1, 4, 2, 2, 0, 3, 0, as well as the 2, 5. These are the edges. The last number that is present, this is nothing but the value for the edge. Basically, this is the edge, right? So we are just reading the edges here, n minus 1 lines until u, v, and w. So this is fine, right? So we are incrementing u here, nothing but we are converting this one to the one based indexing for the internal arrays, right? So this one, line number 115 and 116. Right, so this one g of u dot add and g of v dot add, whatever I have written. So we are going with an undirected graph, right? So we are just adding both the directions with a digit. We are adding both the directions with a digit, right? So this one, right? So finally, we have come to the last part, nothing but here DFS and the get answer. DFS of 1 comma 0 is nothing but we are running the DFS from the node 1 to compute the DEP, nothing but the depth, DN, UP, as well as size SZ and the sun, which I have already explained. We have already written the DFS method here somewhere. First itself, first or second, yeah, yeah, DFS. So this one, right? So this one we are calling the DFS helper method here within the main method, right? So next we are going with a get answer method, which we have already written. So get answer 1 comma 0 comma 1, whatever I have written here, this one we are running the DSU on the tree just to count all the interesting ordered pairs, right? So that's what we are doing with this method. Now let's come to the final part. These two, this is related to the input output. We are just printing the final answer by making use of out.println of ANS, right? Answer is stored in the result variable ANS here. We are just printing the final answer using that variable. And finally, we have to flush the output. We are just going with the out.flush. You can just go with a flush or close, either of them, both of either of them works, right? So this is fine. Now this is it for the code. Now let's do one thing. Yeah, this is it for the code. So before checking the code with the different inputs, let's do one thing. Let's quickly, let me copy paste the signature starter template. Just give me a second here. So I'll just come here. Yeah, let me paste this one. Yeah. Hmm. Yeah, I'll just come to the question. Let me copy this one. The output that we need to get here is 7. Let's check. Hmm. So many errors we have, man. 10 errors. Okay. Where what is expected here? What is this 5, man? Line number 71. We come to the line number 71 here. So this is within the calc, right? Just give me a second here. So what we did there actually within the calc, X is the computed residue matching some letters in the U, right? So this one, why I have given 5 here? So this one has to be modulo, right? Yep. Let me run this one now. Uh, 4 errors are gone, right? This is fine. Again, I have made use of the 5 itself in the line number 79 as well. There is 79. This one has to be modulo M. So 2 errors has to be gone. Yeah. Now, so this has to be not equal to, not minus actually. 101. Let me give you a not equals to. This is fine. The final step is class interface enum or record expected. Line number 144. Let me remove this one. Let me run this one now. We have error. Eh? So many errors again. This is warning. This is fine. Variable in a due is already defined in the method calc. So just give me a second, 1 second here. So let's see what we have done wrong here. So let me come to the universe, this one. So here long x, this is fine. I have forgotten one step here. So if x is less than 0, I'll just give x equals x plus m. So this is very important basically, right? So this is the missing normalization. So this is very important for the negative x. So this one I had missed. So let me add this one. This is fine. This will not clear any error, I believe. Yeah, this is fine. Next one, let's check the same one. Whatever we have done wrong, let's see. Hmm, let me come with a calc here. Hmm, yep. So this one, I have mentioned this one. The same variable name twice. So this one has to be LCA actually, right? So let me run this one. Some of the errors has to be gone. Yeah, 4 errors are gone. So warning is fine. We are left with 2 errors. Error cannot find the symbol of line number 74. Mm, this is fine. So within the get answer, I'll just come to the get answer here. So this one we have get answer VU. Uh, let me give here VU0. This was this I have swapped, I believe. Still we are getting the error. Hmm, in before the main, so this one has to be calc of U and U, not U and V. This is also fine. We are left with only one error. Error cannot find the symbol. We have LCA minus this one UP of line number, same thing, right? Line number 74. We come. to this one. This one is within the calculate this one method, right? So just give me a second here. Uh, what we should do. Ah, where is this 74? UP of LCA minus. So did I give V here? This has to be UP of U. This is fine. Let me run this one again. So we are getting the correct output, right? So yeah, that was the typo actually. So let me copy this one again. Let's check. For God's sake, if I get 8, yeah, we are getting the correct output, right? So this is fine. So we have whatever the code that we have written works absolutely correct, right? So let me copy this one entirely. Now let me hit the submit button, come to the solution part, and let me paste the solution as well, and let me hit the submit button. Let's wait for some time. So yeah, you can clearly see here, and the toast it is showing accepted. The verdict that we got here is accepted, right? So we went with the DSU on the tree. So we went with this one as well. What do you call GCD modular inverse as well, related to the number theory, and we went with the two hash maps as well along with the DSU, right? So along with the pre-computing the values, right? So uh, this is it for the code basically. I hope the solution part is completely clear along with the approach and the complexities, right? For now, this is it. Thanks for watching, guys.